Okay, so the third way that we can represent enthalpy change is using an expression with molar enthalpy, which we have seen quite a few times at this point now. So again, a couple of things to keep in mind when you're representing enthalpy change for 1 mole. It depends on what the focus of the actual equation is. So you may be talking about the delta H for the synthesis of magnesium oxide, then that is what this is in reference to for 1 mole. And of course, typically when we're talking about molar enthalpy, it's found at SATP conditions. So for example, if I'm doing, so actually, if you've ever come across this in your readings or doing some of the homework, if you see something that's discussing the formation of something, so remember the delta H, the little symbols, the subscripts here can be representing or written to discuss the type of process it is. So for example, delta H of combustion, we've seen the delta H of solution before, delta H of vaporization, melting, etc., etc. If you see this little F, it's talking about the delta H of formation, which is another way of saying the synthesis of that compound. So if we're talking about the enthalpy of formation for magnesium oxide, that means that we're basically going to take magnesium and oxygen and do a synthesis reaction for that. And actually, we've already seen that right here. So this is a formation reaction for magnesium oxide. So we have essentially it being synthesized from its elements. Okay, so there's many types of molar enthalpies. So molar enthalpy of solution, we've mentioned these already. Delta H of freezing, neutralization, and then here's another delta H of formation. So I have this a little bit bigger so I can talk about this a little bit more. This chart here that has some examples. So I want you to notice that, remember when we're talking about molar enthalpy, it's really in reference to anything that has a coefficient of 1. So technically, this molar enthalpy of solution could be in reference to anything here, the sodium bromide, sodium ions, or bromine ions, because this is all 1 mole. Delta H for the combustion, for the molar combustion of methane. Okay, and also, I know this kind of goes without saying, but it depends on what the reaction is. Like if we're talking about the combustion of a hydrocarbon, typically the focus is on the hydrocarbon itself, right? Normally, if we're talking about a combustion reaction, we're not really talking about the formation of water, right? We're talking about, well, what is the molar enthalpy for the combustion of that hydrocarbon? But needless to say, the delta H for the molar combustion of methane is actually the same as the molar for these other two. And actually, there is a typo here. This should be, if I'm not mistaken, there should be a 2 in front of that water. So technically, it's the molar enthalpy for methane and for carbon dioxide formation, but of course, the focus typically is on the hydrocarbon. Okay, delta H for the vaporization, and this is methanol. It's 1 molar, so it's automatic. Freezing, right? You have 1 mole of water that's freezing. Now, this is an interesting point. Okay, look at this neutralization reaction. These are both the same neutralization reaction. We have sodium hydroxide reacting with sulfuric acid, right? Making sodium sulfate and then water. But the way that it's balanced depends on what is the molar enthalpy representing. So this first one is the molar enthalpy for sulfuric acid. However, the second reaction is the molar enthalpy for the base, for the sodium hydroxide. So when you're looking at a reaction, it's very important to keep in mind what is the molar enthalpy you are trying to express. And then here we have a delta H of formation. Here we are doing the formation of methanol. And if you notice, we are taking the elements to synthesize that. So it's essentially the molar enthalpy of synthesis, if you'd like to think of it that way. Okay, the last method of doing enthalpy expressions is through potential energy diagrams. So we've actually seen these a little bit so far, looking at delta H of different processes. So in general, the X and Y axis are typically always the same. So your X axis is the reaction progress, right? So the start of the reaction is essentially your 0 mark. And then as the reaction proceeds, we move to the right. And the y-axis is potential energy, right? So you have the potential energy of the reactants and the potential energy of the final products. The difference between those 2 points is what the delta H value is for that particular reaction. So remember that when you break bonds, okay, breaking bonds or forces, it requires energy to be put in, right? Forming bonds is an exothermic process. Energy is released. So in this reaction, it's the difference between all of the energy needed to break the bonds or forces and comparing it to all of the energy released when new bonds or new forces are created. Okay, so we looked at this, I believe it was in the second lesson for this, perhaps maybe the first one. Anyways, we've already talked about this concept before. So what you're looking at here, when we talk about delta H, we're looking at the overall process. If you have an endothermic reaction, that means that more energy had to go in than the energy that had to come out. So the overall delta H here is a positive value. Okay, so notice the products have a higher potential energy than the reactants did. Okay, so if you have an exothermic process, it's quite the opposite. So in this case, the reactants have more potential energy than what the final products do. So the delta H is actually a negative value. So meaning more energy came out than what had to go in to break those bonds. So overall, you have a negative delta H. So these are just examples showing you with the same processes we looked at before. So here's an exothermic process, right? So here is the synthesis of magnesium oxide or the formation of it. So we have our reactants. Because the delta H is negative 601.6 kilojoules, right? We're going to have our products lower than our reactants. If you have a positive delta H, so for example, when we're doing the decomposition of water here, we are going to have 285.8 kilojoules that have to go in overall. So more went in than what eventually came out. Okay, this last page that's here, okay, so this last page is showing a nice summary of all 4 ways of representing enthalpy for these reactions. So I just happened to come across this, and I like the way that it was set up, but it uses the comparison of cellular respiration to photosynthesis. So we have one exothermic reaction and then one endothermic process. Right, so energy is absorbed here and energy is released. So if you take a look at this, so here's the first one. So notice the energy is in the actual reaction. So it's written on the product side. Over here, we have it in the reaction. It's written on the reactant side, right? Number 2, we have the same reaction, but the delta H is written on the side. Because it's exothermic, it has a negative value. Over here, we have our reaction, delta H is on the side, the number got cut off there, it's the same number as this, but it's a positive value because it's endothermic, right? We can write this out as a molar enthalpy expression. So 1 mole of glucose that is going to be doing the cellular respiration process, right? So here's a 1 mole, it releases 2,802.7 kilojoules for every mole of glucose. So same thing here, a molar expression for the photosynthesis reaction. Again, they're using the mole of glucose as their expression for the molar enthalpy. And if we look at our potential energy diagram, right, if we have our products lower than our reactants, that means that there was an energy release. If we have our products higher than our reactants, that means that energy had to be absorbed.